Modern data sets are rapidly becoming too large and too complex to process by traditional means, which is why our customers are turning to distributed processing applications that support the extreme scale of big data workloads. And this is for things like seismic research, search at scale, and especially deep analytics across various industries. But in order to truly support these applications, it's a must to have robust, integrated, and distributed backing storage that supports extremely high throughput. And this is where Qumulo comes in. So in this demo, we will be demonstrating how the distributed nature of the Qumulo file data platform, coupled with the distributed processing system for big data known as Apache Spark, can enable customers to reach incredible throughputs needed to analyze and process extremely large and diverse data sets very quickly. The data set we're going to be processing today comes from our cloud-based monitoring system, where we ingest about 10 terabytes per day of customer telemetry data used to support and troubleshoot customer issues, as well as understand our customer fleet more in depth. This data set is around 4 terabytes total, currently stored in a 1.4 petabyte archive platform comprised of K144s. Our goal here is to understand the health of one of our core components of our data storage, which boils down to the performance of both SSDs and spinning hard drives. What we have here is an 18-node analytics cluster that we've built, comprised of 18 Linux compute nodes leveraging Intel processors with 16 gigs of RAM each. It's running Apache version 3 with Spark, which is connected to the Qumulo file data platform over the network. First thing we're going to do is start an interactive Spark session through one of our Linux machines, where we will start up a Python shell to directly insert PySpark code in order to facilitate the data analysis, ultimately submitting jobs to the Spark cluster. This Python script will parse all of the cloud-based monitoring data, which is stored in .json files, and using the power of Spark on top of the Qumulo file data platform, we'll be able to process 4 terabytes of telemetry data in an extremely short amount of time. After copying in the code, this will tell Spark how to find our data and how to process it in a way that makes it most useful to our data scientist, who is ultimately the end user. Next, we will select about 10 hours of telemetry data from our customer fleet, comprised of 600 million metrics in a .json format. Now, this will take a few moments to apply, but keep in mind we haven't actually started the workload yet. We're still just setting up here. But while we're waiting, we can browse our Apache Hadoop Spark cluster applications, and as you can see, our PySpark shell is active and being used for the data analysis we need to make use of this telemetry data. From here, we can take a look at the Spark user interface, where we can confirm Spark has distributed the work across the nodes in the cluster. And now it's time to actually kick off the workload. The final step here is telling Spark to actually evaluate our code in order to kick off the job, distributing the work across the 18 compute nodes and pulling data from the Qumulo K144 archive platform. And the work distribution has begun, so now let's take a look at our Qumulo file data platform to check out the throughput and some other interesting metrics. So as you can see here, we are already topping out at nearly 9 gigabytes per second of throughput. And keep in mind, this is our archive platform. Through further optimizations in Python code and even faster Qumulo platforms, this number can be much higher. But for our needs, this is plenty fast. Now, if we check out our Qumulo analytics built into the file system itself, we can view the client connectivity analytics. We can see that the I/O is being split across all of the different Spark nodes in our big data cluster. We even provide a way to observe per file view of how throughput is being split within the individual client, providing extreme granularity in troubleshooting hotspots if required. Now let's fast forward just a little bit to the end of the Spark job, which by looking at the graph should be pretty obvious that lots of work is executing against the Qumulo K144s. And it looks like the Spark job is wrapping up now. And that's great. So since we have the job completed, let's run some PySpark queries to pull out useful information from the data frame Spark created for us. Now that we have a data frame, which is a very common abstraction tool used by data scientists to do the data analysis, we can now reference the SSD and HDD drive data we are interested in. The first bit of analysis we can do is summarizing our fleet of hard drives out in the field, which by looking at this output shows we have 62 million data samples, over 100,000 drives, with over 300 billion operations in just 10 hours. We can also do the same as it pertains to latency. It's a useful metric for us internally to understand the overall latency when comparing different drive types, in this case, spinning HDDs versus SSDs. We can see an average of 11 milliseconds for HDDs and 260 microseconds for SSDs. We're also continuing our development with Azure by adding support for page blob storage as well. But finally, let's see if there are any anomalies in our drive latency by looking at some of the slowest drives in the fleet. This would be incredibly painful for our data scientists to dissect without the proper support of a big data ready processing application like Spark. And the better fidelity Qumulo has on anomalous hardware, the better we can proactively serve customers before their own workloads and applications suffer due to hardware issues. So even Qumulo, as a storage vendor, still makes use of big data applications to stay ahead of the curve. It's incredibly important to us, and we definitely believe it's important to our customers, which is why we've done everything we can to deliver high throughput systems that can also integrate with prominent big data applications. Thank you.